Okay, so now we're going to talk about attractive forces. And this has to do with how molecules interact with each other. And so, what is driving that interaction? Well, we call them attractive forces. They tend to cause molecules to attract. Now, sometimes they can, be repulsive forces, but overall it's attractive. And the four I'm going to list, barring an ion, cation interaction, something like that, they're going to be attracting. All right, so, this drives the interaction. Or I'll say interactions between molecules. So we are into the multiple molecule state of things now. And there's 4 of them we're going to talk about in this class. And I'm going to go from high to low. Okay. So, our highest, our strongest attractive force is ion. Oh my goodness. I think I've started every video with a misspelling today. Alright. Ion. And this is exactly what it sounds like. This is something we've seen with ionic compounds. So cations are attracted to anions, and so this is just the attraction between oppositely charged particles, cations and anions. So you have full pluses and full minuses. Okay. An example of this, something like LiCl-. There's an attraction here. So it's not a line, it's an arrow, just to show that there's attraction. So the positive and the negative are attracted to each other because they're oppositely charged. That's what I'm talking about. So next, and so I guess I should also mention, you will only see this in ionic compounds, right? If you have ions, ionic compounds, not covalent. So everything else will show up in covalent compounds. So ionic compounds are held together with a ton of attractive forces. And I'll bring some numbers into play later, but just to bring the point home, we'll talk more about melting points and stuff as well, but essentially, if you see a liquid salt, we have a name for that. Maybe you've seen one in real life, maybe you haven't. But we call it magma. So it's very hot. It takes a ton of energy to melt it because they are so strongly held together and just want to be solids. But we'll get into that more later. But so this is a very strong attractive force. So the next strongest is hydrogen bonding. And this is attraction between OH groups, like in alcohols, or water has OH groups. And so it's an interaction of that H on the end and lone pairs on oxygen and nitrogen and stuff. So between OH groups, or NH and FH also does it. So if you see an OH or NH, FH, that's not really going to show up in nature. So if you dissolve this in water, you get what's called hydrofluoric acid, which is the most terrifying thing I've ever worked with. So most acids burn your skin. Hydrofluoric acid goes straight to the bone and just basically rips the calcium out of it. And so your bones become like jelly. So I forget what Harry Potter movie it was. Well, also it happened in the book. But anyway, he gets all the bones taken out of his arm. And so basically he got hit with the magic version of hydrofluoric acid. If you get a spot on you the size of a golf ball, it's fatal. There's a professor I knew at OSU. He used to work in a chemical factory, and they had to work with this stuff. And they didn't have the treatments they have today, so they have some tricks now that can help a little bit. But back in the 60s, it was just like if they got hydrofluoric acid on them somewhere, amputation. You get it on the hand, at the wrist. You get it on the arm, elbow. You try to save as much of the limb as possible. And he was working with a guy who got it all over his face. And so they all just looked at each other. I mean, they took him to the hospital because they all looked at each other and went, well, we can't. If you cut his head off, that's just murder. So we can't do that. And the guy didn't make it. And when I first heard about this stuff, I was a student, and it was actually a truck driver on I-5 here that was transporting it. And he wasn't properly trained or made aware of the hazards he was dealing with the substance he was transporting on his truck. It looked like it could have been milk or gas or whatever, those big tanker trucks. You got to look at the sign to see what's in there, and this guy wasn't trained to deal with acid. I don't know what he normally trucked, because he had a leak, and he fixed it, and he got some on his hand, and was like, oh, it's acid, I better deal with it. And he went, oh, it's not burning the skin, I guess it's not too bad. So he started driving, and his hand started to kind of throb and hurt. And so then he pulled over, and it had to get him medical attention, and it had already taken all the calcium out of his bone matrix in his hand. So I don't remember how it ended. It's been a long time, but I'm pretty sure he didn't get to keep his hand. Because once that calcium's out, there's no putting it back in, really. Not fast enough to protect everything, so it just becomes amputation. So terrifying stuff, and I had to work with it. I had to boil it and then put something in it. And so I've never been more scared of anything I worked with in my life. I was aware of the hazards. I knew the story of the truck driver already. I knew all that. And then they're like, okay, well, we need you to do some analysis on some stuff. And I was like, oh, sure, okay. And they're like, okay, well, the only way to get this thin film off the glass is to boil it in acid. And I was like, oh, okay, like, do that in the fume hood. There's precautions I can take. And they went, well, the only acid that we know that works is hydrofluoric acid. And I don't think they expected me to know all that meant, because I was working on my bachelor's at the time, and as soon as they saw they had the "you've got to be kidding me" look on my face, they proceeded to explain that they tried every other acid and it didn't work. And so I had to boil hydrofluoric acid, and then I got the longest pair of tongs you could ever imagine, and I would put it in the boiling hydrofluoric acid, and I would still change my gloves. And then when I saw that the glass no longer had the stuff that was deposited on it, I would turn the heat off, I would take the glass out, and then I would very carefully pipette from that container. Oh man, it was terrifying. So that's a real problem. And so now they have what's called, I think it's calcium gluconate gel, or gluconate, something like that. And it has calcium to deactivate the acid before it gets to the calcium in your bones. So that's the trick they have now, is you put this gel on it. So it's a very unique acid treatment. There was a Russian guy who got it all over his arm, and they actually managed to save his arm because they did the calcium treatment, and then they gave him an IV drip with, I think it was a magnesium drip, to up the magnesium concentration in his bloodstream in that area. And I'm not going to say you should look these pictures up, you can't unsee some things, but they're out there. And you can see like the entire vascular structure of his arm, because it all has this stuff precipitated in, like, everywhere. But he managed to keep his arm and his hand. He lived, so it worked. You're really making lemonade out of some lemons there. But so into the stories there is, you're not going to see this much working in the health field, and if you do, run. These are going to come up a lot. NH are very important for hydrogen bonding. And so the reason this works, there's a lone pair on the nitrogen. It might make other bonds. And fluorine has a bunch of lone pairs. And so what happens is these hydrogens, this oxygen has lone pairs on it as well. These hydrogens will interact with the lone pairs on the oxygens, fluorines, or nitrogens of adjacent molecules. So they can kind of, sometimes they can even potentially trade hydrogens and stuff. It gets a little complicated. But this is the strongest attractive force that you will see in covalent molecules. And then we have dipole-dipole interactions. Okay? And so remember, dipoles are from polar bonds, right? You have an area of slightly positive charge, an area of slightly negative. And so this is covalent molecules that have polar bonds and are themselves polar molecules. So polar molecules have areas of positive and negative charge. They're not full positive and full negative, like these ions, just partial and partial. And so they still have attraction, but not as strong. So, you know, it's like when you have two magnets. They're weaker magnets, but they're still going to attract to each other. And so this is attraction between, and this means partial positive. That little delta means partial positive, and so we got partial positive and partial negative portions of polar covalent molecules. Make sure I get all the words in there. Okay, so this is for covalent molecules, this is for covalent molecules, this is ions, and so the last one shows up with covalent molecules as well. And so what if you don't have a polar molecule? So these are all going to be polar molecules up here as well. Hydrogen bonding is occurring in polar molecules that have alcohol groups or amine groups on them that have a hydrogen or hydrogen fluoride. But what if, or if you don't have those groups but you still have a polar molecule, you get dipole-dipole attraction. But what holds together non-polar molecules? Like this plastic, this is a solid, it has a ton of attractive forces holding it together, but it's entirely made out of non-polar molecules. So how do we do that? Well, it's called dispersion forces. And it's probably my favorite one to talk about, but it is the weakest overall. And we'll talk about, well, how do you hold the plastic together? Well, if you add up a whole bunch, like millions of weak interactions, you get a strong interaction. You know, it's like becoming a millionaire by collecting cans. Can you do it? Yeah, but it's a lot of cans. Alright, so you can get a strong overall attractive force by adding up a bunch of small ones, a bunch of dispersion force interactions. But that's why those molecules are so long to be able to do that. Alright, and so this is going to be in nonpolar molecules, dispersion forces. And what happens is you have even sharing electron in a bond, right? But sometimes the electrons are moving randomly still. So on average, 50% here, 50% here. But every now and again, they just end up on one side together. So all the electrons end up over here for a brief moment, just a fleeting moment. But when they do, it's slightly negative here, slightly positive here. Now the electrons are going to return, and maybe it goes the other way. Maybe at some point it's slightly negative here and slightly positive here. The analogy I like to give is it's like looking at the deck of a ship. People are just kind of moving around, and sometimes maybe they're more to one side than the other. Maybe there's a whale over there, so everybody runs to, we'll say, port, because I totally know my sides of ships, to look at the whale. And that leaves them not on, I think it's totally called starboard, maybe? Sure. And no idea where the names even come from. But the other side of the ship doesn't have as many people. And so if those were electrons, they all shaded over here, just for a brief moment. And so slightly negative, slightly positive. And so the same idea that holds together ion-ion and dipole-dipole, it's just a weaker version. So it's still positive, attracts a negative. Positive attracts the negative. But now, not only is it slightly positive and slightly negative, but they're only slightly positive and slightly negative for a fleeting moment, right? So this is, this is like a long-term committed relationship. It's very strong, And then this is like, you've been together a while. Like, I don't know, you have keys to each other's apartment or whatever. And then this is like, it's Friday night, it's 1 a.m., the place is closing. You catch each other's eye across the bar for that moment. That's dispersion force. That moment of attraction. That's all it is, just a moment. And then, you leave with your separate groups of friends. But you notice each other for a moment. That's dispersion forces. It's fleeting. So those electrons all move in a spot. You get uneven charge for a moment, and they move back. They're always moving around. And now the larger a molecule is, the more likely it is that you're going to have uneven distribution because you have more space, you have more electrons, more likely they're going to run around randomly away from each other. Now to be clear, all molecules do have dispersion forces. It's just they get washed out by stronger things like dipole-dipole and hydrogen bonding if they're present. So when we talk about molecules in the future, it's going to be like, oh, which one has the strongest attractive forces? Well, you just look for, what does it have hydrogen bonding and everything else doesn't? Well, then it's hydrogen bonding. If there's an ionic compound, that wins. And I'll talk about tiebreaker, like what if you have 2 ionic compounds? So I'll have a video on that. Okay, so let's get this in writing. So dispersion forces result from a momentary uneven distribution of electrons, and I cannot emphasize momentary enough, distribution of electrons. So that means you get a temporary plus, well, partial plus and partial minus that attract. Okay? So it's momentary, it's fleeting. You get that, you get this effect, this effect right here, but only for a moment, and then it's gone, it zeroes out. And then it happens again, and it's gone, and it happens again, and it's gone. And so it's small interactions. But again, if you have a big enough molecule that's nonpolar, it's enough to, make a solid. So, again, this is the order. So if you see an ion, everything else is covalent, that's going to have your strongest attractive force. If you see a covalent compound, and all the rest of them are covalent, and you see one that has an OH or an NH on it, we're not really going to worry too much about FH, then that's the winner. It has hydrogen bonding. If you have all covalent compounds and there's all nonpolar and one polar, the polar compound is going to have dipole-dipole attraction. It's going to have the strongest attractive forces. And if they're all nonpolar, then you have dispersion forces, and you got to get into the dispersion forces kind of tiebreaker system. And we're going to talk about that. So there's ranking these different attractive forces among each other, and then there's ranking within the attractive force. What has stronger dipole-dipole interactions? What has stronger hydrogen bonding? And I'm going to do that in the next video, as well as show more examples of molecules that actually have these attractive forces. So that's what I'll be doing for the next 4 videos. I'll do 1, 2, 3, 4 videos. So if you're not feeling super keen on them, just from this brief introduction, I don't know how you couldn't. I only misspelled something there, and I have a weird arrow thing there, and oh, I misspelled that. If that's not helping you, watch the next 4, and then maybe come back to this if it's still not clicking, and just cycle through again, or email me, or post some questions on the Moodle page. All right, so we're going to talk about ion-ion interactions next.